Good morning to all of you. So in the last discussion, we were discussing the machining process, and particularly we have started with the single point cutting tool. So we discussed some part of it, what is the method of production of a new surface by using the cutting tool, what are the differences between single point and multi-point cutting tools, and what is the principle of generation of a surface, what are different types of surfaces, generation and tracing, what is generatrix, what is directrix. So we will continue with turning here, and first of all I would like you to introduce with the single point cutting tool geometry. There is a term called the tool designation and or tool signature. So what we do there, we write the elements of the geometry of the single point cutting tool in a particular sequence. So here you can see we have shown a tool. This is the front part of the single point cutting tool. This part is known as shank, and this is fixed in the tool post of the lathe, whereas this part is used for cutting. As you know that the cutting actually occurs along a cutting edge. It has got two cutting edges, so the one which is taking more part or the maximum cutting occurs along that is known as side or primary cutting edge. So side cutting edge is also known as the primary cutting edge, whereas the other one is end cutting or secondary cutting edge. Secondary cutting edge. So this portion of the tool, front part, that is known as face. It has got inclination along two planes. If you view it in this plane, this is the front view of the tool. This is, or if I see this from this side, this will be the front view, this will be the side view, and this will be the top view. So we can mark the arrows. So if you view it from this side, you will find that the tool has an inclination like this. So that is the rake angle. Similarly, we have another rake angle if you view it from this side, and similarly we have the relief angle or the clearance angles, and the side cutting edge angle, and the radius at the nose of the tool. We know that the cutting occurs, ideally it should occur at a point, and that point should be very sharp. That is called the nose of the tool. But actually this occurs along a curved surface which is having very small radius of curvature. So that is known as the tool nose radius. So in all there are 7 angles of tool geometry which we are going to discuss. So before this, let me tell you about these requirements of this shape of the tool. Initially, tool is a prismatic bar. You can say that this is a bar of the tool material. We have HSS, we have high speed steel or high carbon steel, or we have other materials, higher or advanced tool materials like ceramics, etc. So they are ground with the help of a grinder to a particular shape. Initial shape of the tool or the bar used for making a tool is a cuboid, that is known as a prismatic bar. So they are ground to the required shape and held in such a way against the grinder so that we get this type of shape. So the purpose of various surfaces to be produced here is face, means the if I show it here, I explained this in the previous discussion also. This view of the tool, and here we have the surface which is turning against this, or this is center rotating like this to be, and the tool is fed in this direction. So this is the material which has been removed. It flows along this face. So if we don't provide any face, in that case this will flow along a flat surface. So that is also done in case of some materials like brass. We have zero rake angle because the brass is not producing any specific or very high resistance for the removal of the material with the single point cutting tools. There we use the zero rake angle tool, but generally the rake is provided so that the chips, this removed material is called chip, so the chip flows easily. Chip flows easily over this surface without producing much friction. Otherwise, if there is lot of friction, then there will be interaction of the chip material with the surface of the tool, and as a result there will be heat generation. Heat is already produced. We know that maximum amount of the work which is done for removing the material through the machine, that is wasted in heat energy. So in that case, the material of the tool will get cling to that, or it will stick. The material will be removed from this surface if we do not provide sufficient rake, and it will stick to this chip and it will move, so that the rake surface will become like this. It will be a weak surface here and the tool will break. That is known as tool failure. So the rake is provided so that the chip flows easily over it. Then we have the face or the flank. This is the face. Now there are two flanks. One flank, how the flanks are produced? With the intersection of the cutting edges with this edge of the tool. This is side flank, and the other one below the end cutting edge is known as end flank. So why the flanks are provided? The flanks are provided so that the here you can see this is the flank. So if you do not provide the flank, then there will be rubbing of the workpiece against the tool. So to prevent the rubbing of the workpiece against the tool, the flanks are provided. So we have two flanks, side flank and end flank, and flanks are provided by making the provision of the flank, the clearance angles. So they are cleared of the job so that there is no rubbing. Otherwise the flanks will also be destroyed by continuous rubbing, as this metal which comes into contact with this flank, this will through the mechanism of abrasion wear. You know that the types of wears are, one is abrasive wear, other is adhesive wear. So it will enter into the matrix of the tool, and the tool will be, the material at the flank will be removed slowly, gradually, and that is known as flank wear. It actually happens. So this is known as flank wear. So we have face wear, we have flank wear. So that's why the clearance angle and the flanks are provided. Now we have the cutting edge angle. Cutting edge angle is, if you view it from the top side, you will find the cutting edge angles. So they are also provided to strengthen the cutting edges, and a particular type of cutting edge angle is required for a particular type of machining or a particular type of material generally. Otherwise these angles vary within some range. The tool life is affected by all these angles. They can, if you increase or decrease, then the tool life changes. Tool life, what is tool life and machinability, we will be discussing separately. Similarly, we provide some radius at the nose here. This is tool nose, this is nose, and the shape here is like this. So this is the center, so some radius is provided here known as tool radius. If you don't provide the nose radius here, then this point will be chipped off and the tool will fail. So this is why the angles are provided. Now let us discuss the geometry of the tool by making the top, front and the side views. First of all, view from this side. If you call this front view, I am drawing this. This is the horizontal plane, and the inclination of this plane from this is the rake surface. From this horizontal plane it is inclined, and this angle of inclination is known as end rake or back rake, alpha E or alpha B, where alpha E or alpha B, this is end rake, or alpha B, back rake. These are the two names given to this, one and the same thing. Then in this view you can also see the clearance angle. This is the vertical plane. If you draw a vertical line here, this is the vertical plane. Then this angle is known as clearance angle, which is the end clearance angle. We denote this by gamma. So gamma E is and clearance. This is one view, and I can show this plane here also. This is the vertical line showing the vertical plane, and this is the horizontal line showing the horizontal plane. So this surface is inclined to this in this view, and this edge is inclined to this. This is known as clearance, and that one is the rake angle. Then we have another view. If you see it from the side, from this side, then it will look like this. It will look like this if you see it. The rake surface is inclined to this horizontal plane if you see it from this side also. So this rake is called the side rake angle, alpha S. Alpha S is side rake angle, and this is the vertical line showing the vertical plane, and inclination of the edge, this edge of the tool. This is not the cutting edge. One is this cutting edge, this is other cutting edge. So this is flank on this side. So this is the clearance, side clearance. Angle. These are the two views. Then we have the third view, that is the top view. So in top view we will be showing the two cutting edges. The one having small length is known as end cutting edge, the other having larger length is known as the side cutting edge. So side cutting edge with this vertical plane makes an angle that is known as phi s, side cutting edge angle. And we have another plane which is perpendicular to this plane, the edge which is making phi e with this. This is end cutting edge angle. So phi s, side cutting edge angle, and phi e, end cutting edge angle. So these are the elements, and then we have tool nose radius. As I told you that this part of the tool is provided slight radius in place of this sharp nose or a single point. Actually we have this type of nose. So this radius R is known as tool nose radius. So R is nose radius. These are the elements of geometry of a tool, and they are represented in a particular order that is known as the tool signature. So a particular tool signature, in this we write alpha E dash alpha S, then end clearance, side clearance, end cutting edge, side cutting edge, and nose radius in mm. These are the elements of the tool signature or the designation of a particular tool. All these angles have some ranges, and while making cutting tool we select the angles as per our requirement depending upon the material to be cut and depending upon the tool material and the machining process, and then we designate the tool with tool signature. So these angles are written in degrees, whereas the radius is written in mm. So a particular tool signature can be, for example, if it is written like this, this is a tool signature. This designates the angles in the given order. So this part shows how we designate a tool, what are the elements of the geometry of a cutting tool, and how do we explain them, why they are provided. So rake angle is important because this facilitates the chip to move through it over this surface and reduces the friction. Remember that in case of machining of single point cutting tool, machining of brass with SPCT, zero rake is provided. And then relief angle or the clearance angle, so that the two flanks do not have friction or rubbing with the workpiece. And then we have the cutting edge angles, which help in cutting and provide strength to the two cutting edges. And then we have the nose radius, so that the tool chip does not gets cut off, or the tool does not fail at the nose. Now we have certain other parameters, let us discuss those also. One is the chip thickness ratio, the chip cutting edge, and the chip thickness ratio, uncut thickness, and the cut thickness. So let us discuss those. And then we will establish a relation between the chip thickness ratio and these angles. Now before this, let us discuss how the material is removed. What is the mechanics of removal of the material? The mechanics of material removal is through shearing. Shearing, you all know what is shearing. It is just slipping. So the material is sheared by the nose of the tool, and we can show this with the help of a diagram. This is the chip which is flowing over this rake surface. Tool is like this, and horizontal plane, we have this clearance angle of the tool. This is the vertical plane, this is the rake angle, this is the clearance angle of the tool, and we have this uncut workpiece surface. So this thickness is known as chip thickness, T2. T2 is chip thickness, and then we have the uncut thickness of the workpiece. This is our workpiece, this is the tool. This is uncut thickness, T1. And this angle is known as back rake or end rake angle, alpha E or alpha B. Generally we will write this as alpha. This is the clearance angle. So this is the geometry which shows how the chip flows over the surface. So feed is given here in this direction, means this feed is given, or if you don't call it feed, then you can say that workpiece is moving in this direction. So this is our flank surface. This is the rake surface. And this is our cutting tool. The workpiece velocity is v. This is also known as the velocity of cutting. Now the question is, how is the material being removed? The answer to this question is, the material is sheared. This is moving in this direction. So material is sheared here along a plane. So this plane is known as shear plane. What actually is shearing? If you put a certain number of books or cards one over other and then apply a force here somewhere, then the shape of this will be deformed like this. So this deformation, in which the slipping occurs on one plane related to the other plane, that is known as shearing. Shearing nothing but slipping of a body with respect to other. Suppose this is a body like a beam and a force is acting here, and here the resultant force. So it will shear along any plane so that two new surfaces are produced, shearing. Similarly, if you cut a paper with scissors or with hand, you are shearing it. So the shearing occurs along a plane, but actually this is ideal case. The shearing occurs here, shear failure along this plane, and this lump of mass is free and it is moving along this. Then the next comes in, this is the depth we have provided for cutting. Then the next comes in and that is sheared here and it moves. So the chips which are produced here, we will be studying after this how many types of chips are produced. Chip is the material being removed. There are three types of chips produced. One is continuous, other is discontinuous, and the third one is continuous with the built up edges. So what are built up edges? It is the chip when it sticks or when the friction is high, when the rake angle is low, or the material is such that friction is high. High energy is produced in as heat in cutting. Then some part of the face of the tool that is broken and sticks to the moving lump of mass, that is chip, and it gets welded here locally. So as a result, when it is removed along with this chip, then the built up edges are formed. So it makes the tool weak, though it is advantageous to some extent, but only to some extent. So we will be discussing it later on. The continuous chips without built up edges are desirable and they may be broken down with the help of the chip breaker. So actually the shearing takes place along more than one plane that are known as primary and the secondary shear zone. So this is the primary shear zone. Here we have two planes. Here primary shear occurs, and here also we have a plane that is known as secondary shear zone. So the material is removed by the mechanism that is known as shearing, and the shearing occurs here along different planes. There are two planes ideally. One is primary shear plane. Actually these are more than one, so there are two here, two or three, and this plane is secondary shear. So secondary shear occurs along the rake surface of the tool, and primary shear occurs here along the primary shear plane. So this is the mechanism. Now after this, let us discuss the relation among the geometry of the tool with the angles. Or one thing more here I would like to add, the ratio of T1 to T2. T1 is the thickness here. This is also known as the depth of cut provided or uncut thickness. T1 is uncut thickness, also known as depth of cut. T2 is chip thickness. the ratio is equal to R, and R is chip thickness ratio. Also known as cutting ratio. In different books you may find different terminology. Sometimes some other name is given to this term. Now let us establish a relation among these parameters. Let us draw the figure again. This is the shear plane, and the angle made by the shear plane with this horizontal line is called shear angle, phi. Do not get confused with phi E or phi S. Phi is just the shear angle. Angle of the shear plane. Actually what happens, shearing means slipping. So this lump of mass, when it is separated from the material which is cut here, this slips along this. There is slipping. So because of that it is separated along this plane, then it moves in this direction. That's why we call it the shear plane. So this is shear plane, and the uncut thickness, the chip thickness here is T2. The uncut thickness here is T1. If you draw a line, extend this horizontal line, this angle is alpha, and if I drop a perpendicular from this point here on this, so this angle is alpha, this angle is phi, so you will find that this angle is also alpha by using the geometry, and this angle will be phi minus alpha. We can name these O, M. This is normal, this point is P, and this point is say Q. I can drop a perpendicular from here also. This is perpendicular, this point is N. So the angle, if you see, MOP is equal to phi minus alpha. Now we can write in these triangles cos of phi minus alpha. What is cos of phi minus alpha? This angle is phi minus alpha, so base, this is at 90, base upon hypotenuse. So base is OM divided by hypotenuse is OP. So OM is nothing but the chip thickness T2. So you can write OP is equal to OM or T2 by cos of phi minus alpha. Then we can write in this triangle what is sin phi. Sin phi is perpendicular, that is ON divided by OP. ON is T1, uncut thickness, so this gives us OP is equal to T1 by sin phi. So if you equate these two, we get a relation. So you can write from this T1 by sine phi is T2 by cos of phi minus alpha. Equating these two, or T1 by T2 is equal to sine phi over cos of phi minus alpha. T1 by T2 is equal to R. Now you can expand this. So sine phi is equal to R cos phi cos alpha plus sine phi sine alpha. So divide by cos phi on both sides. Tan phi is equal to R cos alpha plus tan phi into sine alpha, or R is equal to, or you can write tan phi is equal to R cos alpha over 1 minus R sine alpha. This is a very important relation which will be used for solving the numerical problems. If we have a zero rake tool, this is back rake or end rake. If we have a zero rake tool, like in case of machining of brass, then tan phi is equal to R. So this is how you can prove the relation. Now after this, in the next discussion, we will be discussing what is the deformation, shear deformation or shear strain. Then we will be discussing the type of edges, how they are produced, under what conditions they are produced, and what then the most important, the merchant circle analysis. What are the forces which are acting during cutting, and how can you do this without cramming it? So you should remember it. We will discuss what is the technique to remember this without cramming it, and then other parts like cutting fluids, what are their uses, and so on. So this is all for today. Thank you.